This is Dr. Miller, and in the last video I discussed the different types of weathering products that precipitate or accumulate to form chemical and clastic sedimentary rocks. For clastic sedimentary rocks, it is important to understand how the solid products of weathering, what we call sediments, are altered as they are transported from places of active weathering to places of final deposition and accumulation. The primary agents of sediment transport are water, wind, and ice, together with gravity. As the sediments are being carried, they are continually being affected by chemical alteration and dissolution, as well as mechanical destruction. As the distance and time of transport increases, the chemically and mechanically less durable minerals are destroyed, and the sizes and shapes of grains are altered. Sediments are said to become more mature as their distance and time of travel increase. So let's look at how grain size can indicate sediment maturity. Near the place of original weathering, newly eroded sediments will tend to be coarse-grained. The larger the grains, the harder it is to move them, the more energy it takes. The smaller the grains, the more easily they are transported. As a result, the smaller or finer grains will tend to be transported farther. Gravel and coarse sand will be deposited closer to the source area than the fine silts and clays. So I will order these classic sedimentary rocks by the size of sediment grains present in them. So these are now ordered from the coarsest grained sedimentary rocks to the finest grained sedimentary rocks. These coarse-grained rocks likely represent deposition near the source of eroding sediment, while these finer-grained rocks were deposited in more distant environments. This order likely reflects how far the sediment grains have been carried from their place of origin. The grain size of the rocks also reflects the energy of the environment in which they were deposited. In a high-energy depositional environment, such as fast-flowing stream, you would expect gravel and sand-sized grains. However, in quiet water settings, such as a lake or a floodplain, you would expect fine silts and clays to accumulate, forming rocks such as these. As sediments are transported, they also change in grain shape. Rock fragments and mineral grains tend to be irregular and angular in shape with sharp edges when first weathered and eroded from their parent rock. As grains are transported, they are abraded and worn. Sharp grain edges are smooth and irregular grains become more elliptical in shape. Thus, sediment grains become more rounded over time. We can easily see the difference in grain roundness between these examples of coarse-grained sediments, coarse-grained rocks. So, in this case, we have a very coarse-grained rock with very large grains, very large rock fragments, but these are all very smoothly rounded and elliptical in shape. By contrast, if we look at this rock, we can see that these individual grains, rather than be smooth and rounded, are very angular with very sharp edges. So the rock with sharper edges indicates a much shorter distance of transport than the one with the rounded pebbles. Finer grained sandstones and siltstones will also show differences in grain rounding when seen under magnification. Another change that occurs with time and distance of transport is grain sorting. Sorting refers to the range of grain sizes within a sediment or within a rock. Well-sorted sediment is very uniform in grain size. All of the grains fall within a relatively narrow range. Poorly sorted sediments are a mixture of both large and small or fine grains. Because water flowing at different velocities will move grains of different sizes, flowing water will tend to separate grains of different size. The farther the sediments are carried by flowing water, the better sorted they become. So let's compare the range of grain sizes in these sediment samples. So if we look at this sample to begin with, we see that it consists of quite large grains, much larger than sand-sized grain, so gravel-sized material, as well as much finer sand and silt grains, all within the same sediment sample. And in this sample as well, contains both coarse grains, coarser than sand size, and coarse sand, again down to finer grains. So this would again be poorly sorted. By contrast, this sample is well sorted, with all of the grains nearly the same size. And we can see the same thing when looking at your rock samples. For example, very obviously in this sample, we have large class, gravel size grains, as well as much finer grains in the same sample. So this would be very poorly sorted. By contrast, in this sample, nearly all the grains fall within a very, very narrow range. They're all nearly the same size. So this would be an example of a very well-sorted sample. Sediments not only change in grain size, shape, and sorting with time and distance of transport, they also change in composition. Remember from the previous hands-on video that different igneous minerals weather differently. The more mafic minerals, such as olivine, pyroxene, and amphibole, are rapidly destroyed by chemical weathering to produce primarily dissolved ions in water. These mafic minerals are rare components of clastic sedimentary rocks because they're destroyed so rapidly. The more felsic minerals, such as feldspar and mica, are more resistant to chemical weathering and will break down to produce clays over time. Quartz is the most chemically and mechanically resistant common mineral and will remain unaltered for very long periods of time. Thus, more mature sediments show increasing amounts of quartz grains. So, let's see if we can organize this collection of sediment samples according to their maturity. This coarse-grained sediment is also poorly sorted. Again, everything from gravel to fine sand. And it also includes a variety of different grain compositions, rock fragments, and even a fair amount of feldspar grains. Rocks formed from feldspar-rich sediments such as these are called arkosic. Somewhat more mature are these relatively well-sorted sands, but they also have a significant percentage of dark mafic minerals. So if we look at this, that not only are there light grains, but there are also a large number of dark grains representing more mafic minerals, that therefore shows that this is a more immature sand. Finally, in this sample, we have a very well-sorted sand of nearly pure quartz. This sediment is highly mature and represents very long times of exposure and long distances of transport or intensive abrasive action. Such sands are typical of beach environments where the abrasive action of waves removes all but the most resistant quartz grains. Rocks formed of such sands as these are called quartz sandstones. These rock samples, specimens, illustrate contrasting maturities. For example, this specimen is very coarse, very poorly sorted, and also has a large number of feldspar grains. These pink grains within this rock are feldspar. So this would be an arcosic rock. So it's not only poorly sorted, coarse-grained, it also has rock fragments and feldspar grains. Although finer, more finely grained, and a little better sorted, this rock also has a large number of feldspar grains within it. So this rock is also arcosic and also immature. So these arcosic rocks, when formed from sediments deposited near, say, rapidly eroding mountains or upland areas. This third sample, on the other hand, is nearly all quartz and is very mature. This rock would likely represent sand transported far from its place of origin and accumulated in a beach environment. So, using what you have now learned about sediment grain size, rounding, sorting, and mineral composition, you can begin to infer much about the origin and geologic history of your sedimentary rock samples.